I want to introduce a little bit of new notation as we do this, as always. Just kind of strip mining our way into weirder and weirder sets of symbols and notation. So we're doing like integral vector calculus in general. And what we realized that, at least if we're just talking about space, maybe you have like parameters that you need to integrate over later in your life. But for now, just think about like, 3D space. There are three things that we could do. We could have line integrals. We could have surface integrals. And we could have volume integrals. And what we've done is, for two of these, written down like, okay, well, what are the properties of the thing that we need, the differential element, and secondly, what sort of like interesting integrals could we write down with this stuff? So for line integrals, we started by saying, okay, there's dr, and that would be a line element, like a differential piece of a line would be dr or sometimes dl. dxi hat, dyj hat, dzk hat. But we could make this more generic, and we could talk about other coordinate systems, because we're going to be spending a lot of time there pretty shortly. So what I could have also said is, imagine that I have some coordinate system, and this will work for the surface and the volume integrals too. So imagine that I have some coordinate system that's given, maybe think about spherical polar for a second, or cylindrical. Is really how I'm keeping track of things is by triplets Q1, Q2, Q3. So there are three kind of generalized coordinates, and it could be something like this. So it could be r theta phi. It could be XYZ, if we're being like boring. It could be weird stuff that you'll get into on this next homework, UVZ, where U and V are parameters of a parabola, so parametric cylindrical coordinates, parabolic cylindrical coordinates. So now, like, basically all the restrictions are off. And in 3D, you just got to give me three numbers, right? So that's really what 3D means. So what would these things look like in a more generic coordinate system? So this is true. Each one is going to have dq1 for the first bit of dq, first coordinate. So they're each going to have their little bit of differential coordinates. What's the problem with, for instance, theta in this coordinate system, or phi in this coordinate system? If I just added these up and put in like a Q1 hat, Q2 hat, Q3 hat, which I'll do, well, hopefully somebody's answering the question. So if Q2, for instance, is theta, why can't I just add all these three things up? What am I missing? Or what doesn't d theta and theta hat have that I would need for a real line element?
You would need to actually like apply the differential operator, and the way you would do that depends on the coordinate system and like the relationship between those coordinates.
Yes,
right?
So specifically, I need an extra thing in front that would actually, if you're thinking about the differential operator as like, well, how much actual distance are you moving by? I need something that bears units. So I need a relationship, in the case of just theta or phi, in between how much theta increases, d theta, and how much actual distance I've moved forward. So we're going to talk about these things and denote them as scale factors. So I need scale factors, h1, h2, and h3. Now they could be 1, just literally the number 1, which they are for x, y, z. So this has scale factors 1, 1, and 1. But for instance, I think we went through both cylindrical, polar, and spherical. Scale factors for this, r is already in units of distance, so I don't need a scale factor for that. In order to turn theta into an actual distance, I need to multiply it by r, so that would be the scale factor. And then got a little bit too bold with that parenthesis. And in order to turn d theta into or d phi into an actual distance, we went through it, and aha, we got to project down into the xy plane. There's like a r sine theta. Okay. And the nice thing about this scale factor stuff and the Q stuff is you have some arbitrary coordinate system. I think there's something like well, I know there are over 20 somewhat common orthogonal coordinate systems made out of weird collections of parabolas, lines, circles, ellipses, hyperbolas. So there should be many more than that. This terminology kind of unifies all of them. Is you pick your 3 coordinates, write down their little differentials, write down their unit vectors. The only thing that's missing is the scale factor that turns you into an actual distance. Okay. So in that terminology, I have d sigma, and I could say that this is true, dq, whoops, 1. Definitely didn't want to do that. dq1 dq2. What's wrong with that? So think about theta and phi, for instance. What's the thing that I'm missing that I need to kind of check out front?
Sine theta?
Yeah, if it were theta and phi, I'd need a sine theta and I need a couple of r's. But in general, I need the scale factors that turn these into actual things that have actual units of distance, like meters. Okay, so not quite. So that would be fine for x and y or x and z or something like that. But if I want an actual piece of area for my surface integral, I would need to actually include something that gives these things actual scale. So this would be h1 dq1. And then h2 dq2. Do that twice. Okay. And not just my notation, this whole scale factor stuff, or Arfken and Weber's notation. Like if you go on Math World, which is basically the large, beautiful online encyclopedia of mathematical entities, is that they'll use the scale factor coordinate system notation too. So I got 3 coordinates. If they don't happen to have units of distance themselves, like x, y, and z do, or r does, you've got to include a scale factor in order to make a good actual bit of actual area or actual line. Okay. So that was just preamble to doing this, because honestly, volume integrals are pretty easy. I have a little piece of volume d tau. It's not, volume isn't directed. So surface, yeah, there's a direction normal to the surface. Line definitely has a direction tangent to the surface. Volume integrals, d tau is a scalar. Okay, so for instance, just rectangular coordinates, what would I write for a differential piece of volume?
Be dx times dy times dz.
Yeah. Okay. And that would have been way too easy, which is why we chose now to talk about different coordinate systems. What about in general? Like I have some arbitrary weird coordinate system that has coordinates q1, q2, q3, and associated scale factors h1, h2, h3.
You could do a similar thing, but also include the product of all the scale factors.
Yep. So I'll write it the kind of pedantic and goofy way once. So the scale factor is the thing that turns this into an actual distance. So dq, q1 might be an angle. So I need to multiply by r sine theta, or something even weirder than sine theta. So it's the scale factor that gives these things actual meaningful units. So in a general coordinate system, not just plain old ordinary Cartesian, I got to do this. And you can put them out front. I think that's what Arfken and Weber tends to do after getting bored with this. Okay, so honestly, that's volume integrals. No weird stuff with cross products, no vectorization, and none of that stuff. So it's just literally multiply your three coordinates, and then if any of them aren't a distance itself, like r or x or y or z, remember that there needs to be a scale factor. Easy as that. So any questions about that? Mostly the notation. You will see this again and again, because basically all of chapter 2 is funky coordinate systems. Okay. Anybody need more time with this before I give you guys a question? Okay. So we'll just kind of keep on this Gauss's law theme, because Gauss's law is really important, and honestly, probably 90% of the volume integrals you will do in your undergrad career are kind of like Gauss's law related. I think the cylinder was more of caused more difficulty than the sphere, so we'll return to the cylinder. So in general, I want to compute a Q enclosed, and there's some funky shape of charge density, and I basically have to integrate up all the charge density. So if you think about calculus as a verb, which is a fine thing to do, to calculus something means to cut it up into billions of little bits and then add those things up, right? Like you calculus up the area under a curve into a Riemann sum or something like that. Okay, so I want to add up all of these little d taus. D tau has units meters cubed if I do it right and I have all my scale factors. How do I get from d tau into a little tiny piece of actual charge q? And the best answer is just like, what are the units of the thing that I need to multiply here? And SI is fine.
D tau is charge per meters cubed.
Yep. Yeah, so if I'm going to get coulombs out and I have meters cubed as my good volume element, whatever goes here has got to be in units, coulombs per meter cubed. Mm-hmm. We're going to call that rho. You're already at the point where we have more physics than letters in both the Latin and the Greek alphabet. This isn't the radial coordinate in cylindrical coordinates. We'll use r for that. This is rho. And so rho is the charge density. And the units of rho would be coulombs per meter cubed. Okay. So that's, in general, how we make a volume integral to get a total charge. So the total charge enclosed is the integral of all the little teeny tiny charges over the volume. And then that would be rho. If we have something crazy, it might depend on our coordinates. Might not be a constant, d tau. Okay. So in general, charge enclosed in some surface or in some volume is the integral over the volume, the charge density, d volume. Okay. So now I want to do that with something kind of interesting. Let's do a cylinder. Call that R naught. Actually, let's call that big R, just so we don't have too many R's floating around. So big R radius, and then height, big Z naught. And we'll put numbers on it just so we get numbers for once. And let's say that this thing has a charge density. Okay, what coordinate system do you guys want to use for this?
Probably cylindrical coordinates.
So cylindrical coordinates are great. So imagine, you could come up with some horrifying scheme where this thing had a charge density that was best expressed in terms of X, Y, and Z. But yeah, probably cylindrical coordinates. So we'll use cylindrical coordinates. And by answering correctly, I got to give you a charge density that's really nicely expressed in terms of cylindrical coordinates. Okay, if you go through the units, this has got to be this constant out front. Just pick 5 so we have a number. Has got to be coulombs per meter cubed. So visualize what this means for a second, is that there's no charge along the central axis of the cylinder, and then as you get farther and farther out towards the edge, then the charge is going to increase like a square. So basically it's got more, maybe you could think about this as a strong dielectric or an imperfect conductor where the charge wants to be at the surface but does it kind of imperfectly. Okay. So you have a charge density, you have a coordinate system, you have the idea that you got to use scale factors. I'll give you guys a couple minutes to start on this and see how far you get, and then we'll get back together and go over the solution. Okay, so I got a volume integral and I got a coordinate system that seems pretty obvious after that discussion. We'll use cylindrical coordinates. This is definitely cylindrical coordinates compatible. And what I have to do is I have rho and it's already expressed in coordinates. So honestly, first task is to find out what d tau is. What is d tau in this coordinate system?
I got R, dr, d phi, dz.
R, dr, d phi, dz. Yep. Yes, and I'll go through the individual steps in that. So we need something that has units of meters cubed in SI. So right off the bat, I can look at the coordinate system and say R is okay, Z is okay. I really just have this phi. So, probably just gonna have to multiply by R. Could be R sine of something, but let's just make sure. So top looking down, so basically what I have is a volume bit that looks like this. So this is a tiny bit of d tau. Okay. So from the top view, what I see is this coordinate d phi is how much differential bit of angle I have. But the problem is it's not like a real coordinate. This is the little bit of arc length I care about. We'll call it ds. I think we'll generically call that s. I want this. I want an actual distance ds. And what ds is through the arc length formula, provided I'm using measuring phi in radians, rd phi. So that's a little bit of actual arc length. And then the other two, just as the units kind of suggest, are exactly what you would kind of think they are. So this actually is a little bit of dr that has the right units. That's how far out I go. So that would be dr, that's okay. This is the tough one, that's rd phi. And then in the up-down direction, dz is dz. That's already rectangular. So top view looking down, just realize that phi needs to be turned into a coordinate or a little bit of arc length that has the right units by multiplying by r. So any questions about that? Okay, what are the scale factors in general for cylindrical coordinates? This is eventually what you'll have like kind of swirling around the back of your head is like I say coordinate system, you guys say scale factors, especially after chapter 2. So the scale factor for r, the first coordinate in cylindrical coordinates, is just 1. Don't have to do anything, just multiply it by 1. What's the scale factor for the third coordinate, z?
Also 1.
Yep, life is great. And then what's the only thing we really need to keep track of, what's the scale factor for the phi coordinate?
R.
R, perfect. Right, so let's put the d's at the end and the scale factors at the front, which is generically how you do this. So d tau is r, dr, d phi, dz. Okay, and then just final triple check after being like really slow and kind of pedantic with all that is this has units in SI of meters times radians times meters, which is meters cubed. Life is good, great. Okay. Any questions about that? Just to put some actual units on these things, let's just say that Z naught is 0.3 meters and R naught is 0.1 meters. So I can actually put some meaningful unity things in there. Okay, so now I have integral volume rho, which is 5 coulombs per meters cubed, r squared, times d tau, and we now know what d tau is. That's r dr d phi dz. And we can do some simplification. So that's 5 coulombs per meter. It's the fifth. R cubed dr phi dz. And then I have limits. We could go from 0 to r naught, 0 to z naught. I'm just going to make sure I order them properly. What are the units on phi, the phi integral?
I chose radians.
Yep, should be radians. And if I want to make this a definite integral and get the entire cylinder, the actual numerical limits should be what?
0 to 2 pi.
0 to 2 pi. And that one's in the second position, so second position. And then 0 to z naught equals 0.3, and 0 to r naught equals 0.1 meter. Okay. Okay, and then just center out. First we do the r integral, should end up with 5/4 r naught to the 4th, and then evaluate that in between 0 and 0.1 meters. And then the other two integrals, don't have to keep rewriting everything, and then proceed that way. So first do the innermost integral, next do the next most inner integral, and then at the end you should get 5/2 pi z naught r naught to the 4th, and then evaluating stuff. Partly just as a reminder, when you do get into I could simplify that into E&M, what your answers might look like. So it would be 3/40 of a coulomb, 3 pi/40 of a coulomb. That's a lot, actually. So a lightning bolt has about a coulomb of charge in it. So stay away from the cylinder. It's kind of scary. Okay, so this is the sort of terminology that we use for the remainder of the quarter, is talking about scale factors and coordinate systems. Most of the time you'll just remember what the scale factor set is for a particular coordinate system, but on the next homework set you will go through one exotic coordinate system just to see how it would be to kind of make one of these things from scratch. So any questions about that? Okay. I am going to just sort of recap what the additional lectures are. Again, part of those are as a resource for you guys to have if there's a homework problem, for instance, that asks you to prove something. This is like the style of proof, and partly because it's like really difficult to write out a lot of this stuff on the whiteboard. But so just like the actual derivative itself, has a geometric definition. So just take df dx, and that's the limit of secant lines as secant lines turn into a tangent line. The vector derivatives, the derivative, thinking integrals, have these basic geometric definitions too. The problem is they're a little bit more obscure, but they're really important if you do actually want to prove something. So analogous to the way that df dx is defined, so limit as delta x goes to 0, limit of secant lines f of x plus delta x minus f of x over delta x. So I have coordinate system, and then I have this f of x that's kind of running through it. And then what I look at is sequentially smaller and smaller secant lines. Then eventually I get to the tangent. Right? So that's the geometric definition of what a derivative is. It's the slope of the function at that point. So these also exist for div, grad, and curl. So the gradient of a scalar function is defined as the limit of a little bit of volume, delta v goes to 0, of integral f d sigma over that little delta v. And the fundamental definition, geometric definition of the divergence of a vector field. Okay, and I can't use v again. Actually, this is the right way of being lazy. Do not use v, use a is my vector field. Again, as a volume, limit as a little piece of volume goes to 0, integral v dot d sigma over delta v, so a little piece of volume. Shame on me. These volume symbols are upside down, which is not good. This makes it look like grad. Just like get in the habit of writing grad, and then that should be an A. What a mess. Okay, so that's right. This actually has a second form that is proven in the additional videos, essentially the divergence theorem. And then we won't prove Stokes' theorem, so I'll write both here. So limit as delta v. So the short story is because we went from a single variable f of x to a vector field, we care about limits as volumes go to 0. And there are a number of different things that you can do within a volume. So you can look at the flow of the vector field out of the surface of that volume. You can compute the divergence of the vector field within the volume. You can circumscribe the edge of that volume because it's with a surface, and then that surface might have a boundary. And I think most of this stuff is self-evident. So we have a volume, and then the volume has a surface. We have volume. Let me put we have volume, the volume has a surface. We have volume, the volume has a surface. This needs to be described a little bit because this is Stokes' theorem, and we're just going to kind of sketch out the proof of that. So imagine that I have a surface. And the best way of describing a surface is think about taking a wire loop, and it could be funky shaped, and then dipping it in soap water and then kind of half blowing a bubble. So that's the sort of surface we're talking about, right? So it's not closed, it's got a boundary. And around the edge of that boundary, this would be the edge of the surface would be a closed contour integral A dot dl. And the surface itself is surface S. So S would be the soap, and then the edge of the surface would be the wire rim of the thing that's blowing the bubble. So that's how you interpret this particular form. Okay, but the important part is these are the analogs of fundamentally what a derivative is. So derivative is a limit of secant lines as they go to a tangent line in single variable. They're equivalent forms for all the stuff we've been talking about. In the stuff I put up on YouTube, I showed how you would prove this one. And if you want to prove it in an arbitrary coordinate system, just throw h's and q's in front of the x's, y's, and z's, and you've got it. Oh, sorry. Yeah, we proved that one. Okay. So after that, just know that these exist. They're in your notes, and we can use them to prove stuff that's really important. So the second analog of stuff from single variable calculus we have is the fundamental theorem of calculus. So there are fundamental theorems of calculus. And I'll put that in quotation marks because that's not what they're called, but it really is what they are. And there are two really important ones for our vector fields. But as a quick reminder, what is the fundamental theorem of calculus? It's essentially the fact that derivatives and integrals undo each other. So I've got this function capital F, and it goes from 2 points, so it's FB and FA. And if f of x is the derivative of f of x, then this is true. Right, this is something that you've used so much it's become like kind of boring. Whoa. Okay, derivatives undo integrals, integrals undo derivatives, blah. Okay, but there's something kind of neat and underappreciated, I think at the Calc 1 level about this, is the fact that I could come up with a whole bunch of different functions that have the same endpoints. And this would be true for all of them. So I could go in a straight line from A to B, right? So the derivative of capital F is super boring. It's like constant, so constant function. But I don't have to do that. I could come up with some other crazy function that's like super wiggly, provided it's a real function, which I may not have drawn. So this also has the same endpoints. So FB minus FA, capital FB minus capital FA would be the same thing. So in some sense, there's a lot of behavior in the interior of this function that just gets completely swept under the rug if it's differentiable, which is to say I can't, I don't break it. So for all the up, I go down. For all the up, I go down is what this is saying. And I end at the same endpoints. So there are vector derivative versions of this. What this is saying in some sense is, as long as you're a smooth or a differentiable function, it doesn't matter what you do at the interior if you have the same endpoints. You're always going to end here, start here. I know that there's as much up as there is down, regardless of like, you know, how much you wiggle. So there is Gauss's theorem, or the divergence theorem. Which says 3D version of that. So I have some vector field A, and I look at some closed, so that's what the circle around the integral sign means, surface S, that bounds some volume V. And this is kind of the same content. So this is relating, if you look at the interior of the integrals, derivative, the divergence is a form of derivative to behavior at the endpoints. So the endpoints, quote unquote, of volume would be the surface that bounds the volume. So same idea, actually kind of got it backwards in some sense, notationally. So this is the end behavior of the function, its integral at the surface, and this is all the wiggling that happens in the interior. So that's what the divergence theorem says. And to draw it, I've got some surface. There's the volume, the surface bounds that. It's basically saying you can have positive and negative divergence all you want in the interior, but then the only thing that leaves the surface is the net flux that's inside. So count up all the sources and sinks in the same way that you count up all the ups and downs of this one-dimensional example, and you will always get the same answer if you have the same number of sources and sinks. So that's Gauss's theorem. We'll do an example of that and then do Stokes' theorem. But any questions about why this might be, for instance, interesting, or just, I don't know, even what the hell I just said? Always a valid question. Okay, the important part for all of these, Gauss and Stokes, is that behavior at the surface or at the line that bounds the surface, behavior at the boundary is determined by adding up all of the stuff in the interior. Right. So this is Gauss's law of electrodynamics, and you guys will relate them on the homework. It's also kind of in the video. Okay.
So this could mean that we don't really care about charge density anymore. Like we could just like look at the like surface of like a charged object to figure out like the total charge enclosed. Like,
exactly. So you could look at the amount of electric field that's piercing some, honestly, like even fictitious surface is how it works. So there's some set of charges inside of this like tied bag, right? So there's the magic bag and it's full of charges. You can figure out what they are, or at least like the sum of positives plus negatives, just by asking questions about how many electric field lines pierce this. So you basically count them all up, count up all the amount of flux going out minus the amount of flux going in, and then that will tell you Q enclosed over epsilon naught. And the epsilon naught is just for physics units. And what you can't do, for instance, is let's say that there's one 10 Coulomb charge inside of there, terrifying, but just pretend there's one 10 Coulomb charge inside of there. And I take it out, manage to survive, and I replace it by a 12 Coulomb charge and a -2 Coulomb charge. Your flux integral, the details might be different, but you would get the same final answer. So all you can tell is the net amount of charge inside of the bag. Or if I were to replace it with, you know, like 10 1 Coulomb charges or something like that. So there's something magical, but there's a limit to the magic, is you can tell me the net amount of stuff inside the net sources and sinks, but you can't tell me a lot of the details of them. And usually the way this works is you do whatever you can do. You either do the surface integral of the flux, or you know the charge distribution inside, or whichever one you find to be easier, honestly. If you do know the charge density inside and details of the flux or electric field. Okay. And yeah, these problems start getting very densely worded. So I need to tell you a surface, and it's got to be a closed surface because we're talking about Gauss's theorem. So Gauss's theorem says, sure, we'll just keep calling it A. Closed surface integral, it's got to be a sealed bag. So you count all the flux lines. Satisfies this. And we'll use this as our function. Okay, that's your vector function. You're welcome. So let me draw the hemispherical shell. So project a circle, the unit circle, down onto the XY plane. Actually, the easiest way of saying it is take the unit sphere, and the unit sphere is full. So it's like a solid 1 unit big bouncy ball, and then just like cut it in half and put it on the XY plane. So that is the hemispheric shell of radius 1 above the XY plane. Okay, so how about this? We'll do one together and then we'll leave you guys to do the other one. Do you guys want more practice with surface integrals or volume integrals? Or do you want me to do the surface integral or the volume integral?
I vote surface integral.
I saw nodding, so motion is carried. So we'll do the surface integral. So what comprises the surface? Remember, it's a closed surface. So how many pieces do I have to worry about? So remember we had,
yes.
Say again?
Like pieces of the surface, or
Yeah.
like, yeah, so there's just one. So it's like the dome and then like the flat bottom of it.
Exactly. So we have to worry about the dome, we'll call it the top. The dome is good, actually. So the dome, and then the bottom, or base, whatever you want to call it. And we got to worry about both because it needs to be a closed surface. So no leaks, no holes, no nothing. And so for the dome, I need to come up with A, and A is just X, Y, Z. Pretty happy about that. What is true about a little piece of d sigma for the top of this.
It's not very fun to write in Cartesian coordinates.
That is the perfect answer, right? So depending on where we are at points up or at points like out and kind of towards the front, so maybe we would like a different coordinate system. What would be the best coordinate system? And it's going to be, so the coordinate system to use for the bottom is clearly going to be Cartesian, because the d sigma is just going to be negative dz k hat, or negative dx dy, but pointing in the negative, sorry, dx dy, but pointing in the negative k hat direction. Just to say Cartesian is down, it always points down. Cartesian is fine, it always points down. But this, I think maybe spherical coordinates would be much better. So our choice, this is a nice example where you would use two different coordinate systems for two different parts. So how do we express the surface? Well, what's true about x squared plus y squared plus z squared?
It's the radius squared, right?
Exactly. And what is this radius for this hemispheric shell?
1.
1. Right. So this is essentially the defining, the parameterization of the surface. Right. So we're basically looking at the surface of radius 1, or x squared plus y squared plus z squared equals 1. Okay. And then we'll call this R. And then what defines our little bit of, no, it should be lowercase r if I want to keep with convention. What defines our piece of area integral? So our d sigma. So do we have any dr? So essentially this question is, what are the two dimensions where the surface is moving?
My guess is that I would do the switch to spherical coordinates first and then express it, I guess, in terms of the two angles, theta and phi.
Yep. So when you move along the surface, you're moving in d theta and d phi. So the coordinates would be d theta and d phi. Okay. What do I need as far as the scale factor goes? You guys remember at this point what the scale factor for d theta is?
It's r sine phi, right? Because it depends on how far up the sphere you are.
So let's see. So we can do this right. So if we take a little bit of d theta, that you can spin all the way around the North Pole. So the latitude is just r d theta. It's the longitude that gets projected down into the xy plane. So it's, if you want to make a little bit of distance out of d phi, it's got to be r sine theta d phi. So that's the funky one.
Okay, I got it backwards.
Yep, and then this one is just r d phi. So you get r d theta and then r sine theta d phi, or r squared sine theta d phi. Okay, the good news is by the end of this course, actually, Yeah, in between this and classical mechanics, these will be just engraved into your brain. Okay, what I'm missing is the direction. Which direction does this thing point? And to some degree, this is what all the work was there for, because now this points in like a really nice direction in spherical polar coordinates.
In the radial direction?
Yes, so we'll call this r hat. So this defines d sigma, okay? So keep this r squared equals 1, r equals 1, r squared equals 1, and r squared equals x squared plus y squared plus z squared. Defines the surface, and this in the back of your mind. So if I want to integrate this function over the entire dome, I'm going to have this magical realization, and you could do it the hard way or the easy way. The hard way would be to convert x, y, and z into their cylindrical or spherical polar equivalents. I'm going to have kind of an epiphany about this. What is the vector x, y, z? It's the first vector you probably ever talked about in physics class in mechanics. So it just so happens to be expressed in terms of Cartesian coordinates here. But if I tell you a triplet of numbers x, y, z, what am I actually telling you? So that is the vector that goes from the origin to the point that I care about. So this is just the position vector, right? So it's the vector that goes from the origin out to here, but then all I care about, because I'm integrating it over the surface, is my sphere. What does the position vector that goes from the origin to the edge of the sphere look like in spherical polar coordinates? You realize like life is really nice.
Just r theta phi.
So yes, I like the r. So that's the distance in between the position. You would have to give me the triplet number, the triplet of r theta phi. But here's the magical part. Which way does this point? Which way does the position vector that goes from the origin to the hemispherical shell always point? Does it point in any theta direction or phi direction?
Nope.
No, it only points in the r direction. So this is our r hat. That's the position vector. This is really nice, right? We could have a velocity component going in theta hat or phi hat, but the position vector goes from the origin out, directed away from the origin by definition, and that's the r direction. So you guys made two really good choices. One is to use a different coordinate system, and the other one is to ask me to do the surface integral, because that's tough. The other one's going to be pretty easy. Okay, does it make sense why this is true? It's like not an obvious thing, and then it clicks, and you're like, oh, okay, yeah, it is literally, this is the position vector, x, y, z, and this is the position vector in spherical polar. Just go from the origin outwards, and r hat is from the origin outwards by definition. Cool. Excellent. So that was all the hard work. Now we're ready to just kind of crunch through stuff. I have integral over the dome A. A is now our r hat. I love it. And then we dot that with d sigma. D sigma is scale factor for theta and scale factor for phi, and then theta and phi. And then that's also r hat. So the r dot r goes away. And we're left with r cubed sine theta, d phi. Okay, what can I do with what can I do with all three of those r's?
Take them out of the integral.
Yes, because they're constant, right? So I'm on this hemispherical dome. In fact, I can take them out of the integral. So it doesn't even contain the integral, but I can also replace them with a numerical value. Specifically, the numerical value of
1.
Yeah, right? And that's just because we're on this unit sphere. So that's really nice. And then we have integral sine theta d phi, or d theta d phi. What are my phi limits and what are my, what are my theta limits and what are my phi limits?
Um, 0 to pi, and then 0 to 2 pi? Or am I backwards?
Nope. Right direction. There's one, so I think you did the whole sphere. So the whole sphere, I go from
0 to pi over 2.
0 to pi, and we're just doing the half sphere. So the only little change is that the theta integral is actually from 0 to pi over 2. Okay, and then math happens, and that equals 2 pi. I will tell you why I should have known it was equal to 2 pi a little bit earlier, is that once you realize that this doesn't contribute anything, it's just like a 1, all that I'm left with here is the area of the hemisphere, right? It's not multiplied by anything aside from 1, so this is just 1. So this is literally just dA, the area of the hemisphere. What is the area of shell of radius 1 that's like a hemisphere, half of a shell? It's 4 pi over 2 or 2 pi, so good. Okay, that was the hard one. Now we've got the bottom part of this. So anybody need more time with that before I clear the screen? Okay. So lots of hard work, that's equal to 2 pi, and then we're left with the integral over the bottom. Okay, remember the two things that we needed? We needed to evaluate A along that surface, so we needed the parametrization. What's true about the surface of the bottom? So how would you describe that? So X and Y can change, but what's true about Z?
Z is 0.
Yep, so the XY plane is the surface described by Z equals 0. Okay, what is the volume or the surface element d sigma for the bottom? So which way does it point for a closed surface? Oops. So the most important thing is to start by just really visualizing what the area is. So you've got the bottom of this closed hemisphere, and maybe somebody pantomimed it, but I wasn't looking at the screens. Which way does it point?
Down.
Down. Okay, and then numerically, how would you, or symbolically, how would you describe down in, so Cartesian coordinates are going to be great for this. I would call that the what direction? So that is the negative k hat direction. And then I can move a little bit in this direction. So that's dx and then dy. So dx, dy minus k hat. Okay, what's really nice about taking the scalar product of our surface with d sigma? What's this whole integrand going to be? So here I have something with I hat component, right? This is x I hat plus y j hat plus 0 k hat, unmixing the terminology. And then I'm taking the dot product of that with 0 I hat plus 0 j hat minus, really, dx dy k hat. And that gives me what? So you can't let like the little differentials scare you. So I've got x matched with 0. That's the I hat and the I hat piece, right? So I hat, so that's nothing. And then y matched with 0, j hat, that's nothing. But then what happens to the k hat parts?
0.
Something and nothing. So this whole thing actually is 0. So integral 0 over, I don't even care, dx dy is 0. Okay, so there's kind of a geometric meaning of this, is that if I were to look straight down at this hemisphere, so here's the z-axis kind of coming right for me, is that all of these vectors in the xy plane, they've got no z component. They've only got x and y components. So I'm going to be looking at these vectors that kind of look like this. And when I dot product them with the area element, I get nothing. Right? So it's okay if that intuition or visualization isn't quite there yet, but it will be. So after all of that work, this is what we get for the closed surface integral. Okay. Any questions about that? Okay, we do have time to do the volume integral because it does take 1 minute. And as I said, you guys chose really wisely. So the volume part, so the divergence bit, first what I need to do is calculate del A. We don't even know how to calculate the divergence in non-rectangular coordinates at the moment, so we really need to use rectangular coordinates. What is the divergence of the vector field x, y, z?
Is it 1, 1, 1?
Yep, so dx by dx is 1, and then matching y with y, d by dy of y is 1, and then matching z and z, dz is 1. So the whole thing is 3. Okay, what's the integral of 3 over this half volume? Well, that's integral 3 d tau. I can pull the 3 out. And that's just 3 times the volume of that thing. What's the volume of half of the unit sphere? That's 3 times 1/2 times 4 pi over 3, which is equal to 2 pi. Right. Easy enough. Okay, so this is what should always be true about the problems that you'll see, at least in physics class versus math class, is that the hard part, like 90% of the difficulty of the integral, is setting the thing up in the first place. And by the time you're actually evaluating stuff, you should, our goal is not necessarily to throw like, hyperbolic arctangents at you, because you can just look them up in Wolfram Alpha. The goal is to actually like look at an actual physical thing, and your job is you got to choose the coordinate system that best describes it, and then express the integral in terms of that coordinate system. So we got 2 pi for the surface integral, the flux through the surface, and then we got 2 pi for the stuff contained within it. So any questions about that before I let you guys loose on quiz number 1? Okay, so we'll do things this way. If you have a question, just do things in the actual chat, just in case sound might be disruptive. And then if it's a good question, I'll repeat and announce the answer to everybody else. Okay, so I think you guys should be able to see either in the file section, or if you go into assignments quiz 1, you should be able to bring up the PDF, but then I'll also just bring it up on the shared screen. Won't need a calculator for this one, but your half sheet of notes and blank paper is okay, and there should be file uploads that are open until like 10 minutes past, just in case somebody gets caught with anything. So, all right, good luck.